So today we're going to continue with our unit on bonding and talk about resonance. So we just finished talking about Lewis structures, okay, and sometimes there's more than one Lewis structure for a compound. So for example, if we looked at NO3, one Lewis structure shows one double bond and two single bonds. So if we do that real quick, we'll end up with something that looks like this, and then some lone pairs. Okay, and that's one form of the Lewis structure. Research shows that all bond lengths are the same for the NO3 structure, and that the strength of those bonds is between that of a single and a double bond. So what this tells us is that there's got to be some other arrangements that are giving this, average bond length between, our double and our single bond and that average bond strength. And so what really happens is that there are three valid Lewis structures for the NO3 compound. And the correct structure is not given by any one of the structures, but by the superposition, or what we're going to call the average, of all three. And so this is what resonance is. Resonance is when there's more than one valid Lewis structure for a particular molecule. And we represent resonance structures with double-headed arrows. So let's draw our other two resonance structures. We could also put the double bond on our more left oxygen atom. Now I'm going to kind of skip drawing all the lone pairs on the non-central atom just for the sake of time. And then we've also got a third Lewis structure where we can put the double bond on that bottom oxygen. And so all three of these Lewis structures are correct. And we say that the electrons are delocalized, which means they can move around the entire molecule, which is why our bond length and bond strength is an average between a double and a single bond. Those electrons are constantly moving, so we could have, flipping between any three of these Lewis structures, basically. Okay, so let's look at an example. So we're going to describe the electron arrangement in the nitrite anion using this localized electron model that we talked about. So first we need to draw our Lewis structures. Nitrogen donates 5, oxygen donates 6, but we've got 2 of them, and then we have a -1, so we know we're going to add another one. So that's 12, 13, and 5 gives us 18 electrons. Because we have 2 oxygens, let's put nitrogen in the middle. And so let's satisfy the octet rule for everything first. Now let's count up. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I know if I have too many, then I need to share more electrons, so that means a double bond. And so we'll just cross them out. So now let's have them share a pair instead, and because this is an ion, we're going to want brackets. So now if we count up, we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, but because this double bond is on the more right oxygen, we could also have a second resonance structure. Remember, we want those double-headed arrows. And so we could put our double bond on the more left oxygen, and both of those would be correct. Okay, so sometimes we're going to run into what are called odd electron molecules, because nitrogen donates 5 and oxygen donates 6, and that gives us 11. And if we're trying to form pairs, that doesn't really work because we have this lone electron, and that's not going to work out. So we need a more sophisticated model than the localized electron model and then just drawing, those Lewis structures. And so we've come up with what's called formal charge. And so it says molecules or polyatomic ions containing atoms that exceed the octet rule often have many non-equivalent Lewis structures, but all of them are following the rules. So we need to figure out, which ones are going to be more correct. So by non-equivalent, we haven't seen any of these yet. The other Lewis structures that we looked at that had resonance, the double bond would switch to a different one, and the bond strength and bond length would be an average between like a single and a double bond. But we'll look at some other examples where we would call them non-equivalent. So we've got lots of different arrangements, and we need to figure out which one is more correct. So for example, we're going to look at a sulfate ion. It has a Lewis structure with a single bond and then one that has several different double bonds. And so we will call those non-equivalent. And so we need to select the most appropriate Lewis structure. And so we're going to estimate the charge on each atom in those various Lewis structures and then look at those formal charges is what we're going to do. So this is where formal charge comes in. So it's the difference between the number of valence electrons on the free atom, so the atom by itself, and then the number of valence electrons assigned to the atom when it's bonded in a molecule. And this will be based on the different Lewis structures that we'll draw. And so this is used to determine the validity of the Lewis structure. So we'll go through some examples and kind of work through this. Okay, so there's some things that you need to know. First, you need to know the number of valence electrons on the free neutral atom. And that's just going to come from the group number, just like we've done for all of our Lewis structures. Then you also need to know the number of valence electrons belonging to the atom in the molecule, and this is where drawing the Lewis structure is going to become important. So to calculate our formal charge, we take the number of valence electrons on that free atom minus the number of valence electrons that are assigned to that atom when it's bonded in a molecule. And so we're going to make a few assumptions. First, we're going to assume that any lone pairs are going to belong entirely to the atom in question. If there's a lone pair on it, it belongs just to the atom. It's not being shared or moving around. Shared electrons, we're going to say, are divided equally between the two sharing atoms. So if we have a single bond, then we would say that they each are getting one of those electrons. And so to find the valence electrons that are assigned, we would take the number of lone pairs on that atom, because we're assuming that each atom gets its own lone pairs, plus 1/2 times the number of shared electrons, since those are going to be split in half. Okay, so we talked about this sulfate ion. Let's look at its several different Lewis structures. Every Lewis structure for sulfate is going to have 32 valence electrons, first of all. It's just, how are they being arranged? And where this becomes more difficult is because sulfur is, I believe, a period 3, and so it can accommodate more. Okay, so first let's look at that single bonded. So we have sulfur, oxygen, oxygen, oxygen. Oxygen, because sulfate is SO4 2 minus. Let's do our lone pairs. Alright, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28, 30, 32. Okay, so we're good, and it is an ion, so technically brackets charge. Okay, so let's look at each oxygen. We know that the valence electrons for just the free oxygen are 6, because that's just coming from the group number. So now let's look at the assigned. So we're taking the number of lone pair electrons. Remember, it's not lone pairs, it's lone pair electrons. So because we have 3 pairs, that's 6. And then you can either take 1/2 times the number of bonded electrons, or you can just count up the number of bonds, because one bond is 2 electrons, and so you're kind of incorporating that 1/2. And so I would just count this as a 1, because there's one bond right here. And so it's 6 plus 1, which gives us 7. And that's the assigned valence electrons. So now if we look at the formal charge, we know it's the number occurring in that natural atom, free atom by itself, minus the number of assigned. And so that gives us a -1. And because each of these oxygens is the same, basically, then they all have a formal charge of -1. And so let's look at that sulfur atom. Well, the sulfur, if we're looking for the number of valence electrons that are assigned, it has 0 lone pairs and 8 shared electrons, or 4 bonds. And so its assigned is going to be 0 plus 1/2 times 8, or since it has 4 bonds, we just make that a 4. And so that gives us a 4 for the assigned valence electrons. Sulfur has 6 in its free state, so 6 minus 4 is going to give it a formal charge of 2. Okay, so let's look at a second structure. Same number of valence electrons, but now we've got different bonds on those oxygens. So we've got 2 oxygens that have a double bond and 2 that have a single bond. So we have a sulfur, oxygen, oxygen, because remember it can accommodate more than 8. Okay, so let's just count out, double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So it still works, but sulfur's got a lot more because it's in that 3rd period and below. So if we look at the oxygen atoms with the single bonds, these two are identical. They've got 6 lone pairs, and then they're sharing 1 bond. So their assigned is 6 plus, the 1 bond, so that gives us 7. And basically they're going to be the same as the previous Lewis structure, because they've got 6 lone pairs in one bond. So each of these are getting a formal charge of a -1. So now if we look at the ones with the double bonds, we've got 2 lone pairs and then 2 bonds or 4 shared electrons. And so here's our lone electrons, and then minus 2 bonds, plus 2 bonds, so that's going to give us 6. And we know that the formal charge for these is 0 because here's that free atom, here's the assigned valence electrons, and so these get a formal charge of 0. And then if we look at the sulfur, it again has no lone pairs, but this time it's got 1, 2, 3, 4, 5, 6 bonds or 12 shared electrons. And so the assigned for this one is 0 lone pairs plus 1/2 times 12, or that's 6 bonds, so it gives us 6. Excuse me. And so then we can calculate the formal charge for sulfur. Here's the free valence electrons, here's the assigned valence electrons, and that gives us a formal charge of 0 as well. So if you notice, this one has a lot more formal charges of 0 and a couple negatives versus the previous one where the formal charge on our sulfur was 2. And so that's going to come into play in a second here. We're going to assume that atoms and molecules try to achieve formal charges as close to 0 as possible. And if they can't be 0, they would like to be negative. And those negative formal charges need to reside on the more electronegative atoms. And so because of these assumptions, the structure with the 2 double bonds and the 2 single bonds is going to be preferred because we had excuse me, more formal charges of 0, and the ones that were -1 were on the more electronegative atom. And so that tells us that that's the more correct Lewis structure, even though they both follow the rules. And so then from there, we would say that sulfate has 2 resonance structures. So it has the double bonds on, I guess we could say the horizontal oxygens, or it could have the double bonds on the vertical oxygens, basically. So that other resonance structure with all the single bonds, we're not going to include that anymore because we're going to say it's less correct. So this is the more correct structure. Okay, some rules governing formal charge. So to calculate formal charge, like we already talked about, sum of the lone pair electrons plus 1/2 the shared, or just count out the bonds. And that's the number of valence electrons assigned. And then we subtract number of assigned from number of valence electrons in the free neutral atom, and that gives the formal charge. And the sum of the formal charges of all atoms in a given molecule or ion have to equal the overall charge. So if it was a molecule and you added up all the formal charges on all the atoms, it should equal 0. And for an ion, it should equal the charge on the ion. So for the sulfate ion, the charge was -2. And if you go back to the formal charge for the one with the double bonds, 2 oxygens were -1, and so it would give you a total of a -2. So if we have non-equivalent Lewis structures, those with formal charges close to 0 and with any negative formal charges on the most electronegative atoms are going to be the best. And that's why the sulfate with the double bonds was a better Lewis structure than the one with all single bonds. Okay, so give possible Lewis structures for XeO3 and then which one would be most appropriate. This one is kind of crazy. There are a ton of Lewis structures, and then they all have resonance. So we'll just look at a couple real quick. So we could have, first of all, we could have all single bonds. Oh, and if we add it all up, we should have 26 because xenon's 8 and then each oxygen is 6, so that should give us 26 electrons total to work with here, valence electrons. So if we do all single bonds, this does come out to 26. And then if we do the formal charge, so we've got 8 free valence electrons for xenon minus it's got 2 lone pairs and 3 bonds, so that gives us a formal charge of 3. So right away we're probably not going to look at this one as being correct because its formal charge is really high and positive. And then if we look at all these oxygens that are single bonded, we know we've got 6 free minus 6 lone pairs plus 1 bond, and so that's going to give us a -1. No resonance structures for this one, so if we go on to the next one, remember xenon's way below period 3, so it can accommodate more than 8 valence electrons. And so that's what we're going to see in this next one, where we could have a double bond on one of the oxygens, and then resonance, it could be on the bottom oxygen or the right-hand oxygen, and so that's where our resonance is going to come from. And so if we use up our 26 electrons, we end up with a lone pair still on the xenon. So we have 8 free minus, let's see, we've got 2 lone pairs and then 1, 2, 3, 4 bonds. And so our formal charge is now 2. And then these single oxygens are just like the previous one that we did, so -1 and -1. And then for this oxygen, 6 free minus, let's see, 4 lone pairs and 2 bonds. And so we've got a 0. So this one's pretty good, but then we've still got -1s and 2s. So then if we go to the next type of Lewis structure, we could have 2 double bonds. And then, we could have some resonance within that. And then we've got a lone pair on the xenon. Okay, so we know we've got these double bonded oxygens. It's the same as the one over here, so we know formal charges of 0. Our single bonded oxygen formal charge isn't going to change, so now we just need to look at xenon. So 8 minus, let's see, 2 lone pairs and 1, 2, 3, 4, 5 bonds. So that's going to give us a formal charge of 1. So we're getting closer to something that's good. But there's another Lewis structure. It's like never ends with this thing. And so basically we could have all 3 of them double bonded. And I haven't been checking the valence electrons, but if you check, they should all add up to 26. So let's just check this one real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then lone pair, so 26. So we know that all these oxygens are going to have formal charges of 0 because they haven't changed from any of the other double bonded oxygens. And then if we look at xenon, 8 free minus 2 lone pairs and 1, 2, 3, 4, 5, 6 bonds. And so that gives us a formal charge of 0. And so this Lewis structure is the best because all the formal charges are 0, and that's the ideal situation. And so the rest we would say don't actually occur. Okay, so before we get started with the check for understanding on formal charge, I completely forgot about Chemistry Cat, and I'm sure you have been missing it. So here's another Chemistry Cat joke. It's pretty good. You can pause if you want to appreciate it more. But let's go on to check for understandings for resonance and formal charge. So number 1, what is resonance and how is it represented when we're doing Lewis structures? Number 2, what does it mean to say that electrons are delocalized within a Lewis structure, and how does this relate to resonance? Number 3, what is the purpose of using formal charge, and how is formal charge calculated? And number 4, what are the 2 assumptions made when using formal charge to determine the best Lewis structure? So give these a try. We'll discuss them in class. Have a good day.